Consider the physics of a climbing rocket, a discharging electrical capacitor, and a server queuing algorithm. They operate in completely separate engineering realities, yet their core behavior is connected by a single mathematical rule. These are all examples of dynamic systems. In engineering, a dynamic system is any scenario where a specific quantity changes relative to its current, ongoing state. Take aerospace engineering. As an aircraft climbs, the rate at which atmospheric pressure decreases is directly proportional to the pressure itself at that altitude. In electronics, an RC circuit behaves the same way. When a capacitor discharges through a resistor, voltage drops at a rate proportional to whatever remains. In computing, cloud architecture faces a similar problem. During traffic spikes, the rate of change in server queues scales dynamically based on the existing load. Despite operating across entirely different physical mediums, air pressure, electrical current, and data traffic, the rates of change in these systems are governed by the exact same structural syntax. Look at these three specific rate equations side by side. dP divided by dH equals negative Kp for aerospace, V prime plus V divided by RC equals 0 for circuits, and V prime equals negative Kv for computing. By stripping away the specific physical variables, pressure, voltage, and velocity, all three reduce down to a single master format. Mathematically, this is a first-order, first-degree ordinary differential equation. It involves only the first derivative, raised to the power of 1. Mastering the structural logic of this single equation provides the mathematical toolkit required to build predictive models across all major engineering disciplines. To solve these dynamic equations, engineers rely on identifying specific patterns. The primary analytical method is finding a variable-separable structure. The mechanical goal here is pure algebraic isolation. We want to sort the variables. This animated diagram shows the aerospace atmospheric pressure equation, which we will use as our primary test case. Using basic algebra, we group all identical variables with their respective differentials on opposite sides of the equal sign. P and dP move to the left, while the altitude variable h and its differential dH move to the right. Once the equation is cleanly factored and separated, the calculus can begin. We perform integration on both sides simultaneously. Resolving this specific integration yields a standard mathematical format, a general exponential function. When we map that formula back to its physical meaning, it produces the exponential decay curve necessary for calibrating altimeters and predicting pressure loss over altitude. This exact same variable separation workflow directly solves the electronics example for RC circuits. A discharging capacitor will follow this identical exponential curve, dropping voltage predictably over time. However, while variable separation successfully creates a structural model, the math is incomplete. Indefinite integration leaves us with an ambiguous constant, preventing the formula from being a precise, usable physical tool. The result of our previous integration is mathematically defined as a general solution. This chart plots the problem. Because we used indefinite integration, the equation inherently produces an arbitrary constant of integration, known as c. This creates an infinite stack of parallel exponential decay curves on the graph. C represents an infinite family of possible realities. An equation this broad cannot be used to engineer a physical system. Physical hardware does not exist in arbitrary states. It has absolute, measurable starting parameters. To lock our mathematical model into reality, we apply boundary constraints. In our circuit example, if we know the exact voltage of the system at time 0, we establish a constraint. Watch as the infinite stack of curves collapses into one single absolute path. Plugging this known boundary constraint into our equation allows us to definitively solve for the constant c. With c defined, the general formula becomes a particular solution. Applying boundary constraints removes the theoretical ambiguity of calculus, yielding a functional specification that can be used to build a physical altimeter or a precise timing circuit. There is a major limitation to the variable-separable structure. Often, a rate equation's variables are too entangled to separate via basic algebra. Look at this complex differential equation. The x and y terms are mathematically locked together. You cannot pull them apart to integrate them. For these stubborn systems, engineers use a secondary manipulation method, the homogeneous structure. To use this method, the equation must pass a strict rule. As highlighted here, the total combined degree of the variables in every single term must be mathematically identical. If the degrees match, we apply a core structural trick. We substitute the y variable with a new proportional relationship, y equals vx. Substituting y equals vx also forces the derivative to expand into a new form. dy dx becomes v plus x dv dx. We drop both of these replacements into the original equation. This specific substitution triggers a mathematical payoff. It forces the tangled equation to reorganize and collapse back into a cleanly separated state. This exact homogeneous logic governs the buildup of current in RL circuits, dictating how quickly motors and solenoids energize. The homogeneous method does not solve the ODE on its own. It is a structural trick designed purely to force a complex system back into a manageable, separable format so integration can proceed. In modern computing environments, the execution of these systems shifts from manual algebraic derivation to software automation. Engineers rarely perform variable separation or homogeneous substitutions by hand when dealing with complex multivariable simulations. This Python code snippet shows a programmatic solver. Specifically, it uses the SymPy library and its dsolve function to handle the mathematics. The dsolve function automates the exact structural identification and variable separation logic we just derived manually, executing the algebra instantly in the background. The solver generates the general solution, seamlessly applies the boundary constraints provided in the code, and outputs a highly precise physical model. Look at this physics engine simulation. When calculating aerodynamic drag on a moving object, the deceleration is proportional to the object's velocity. To make the object slide to a halt realistically, the software constantly evaluates precise first-order ODEs frame by frame, updating the velocity and position instantly. Whether calibrating a rocket's trajectory, timing an RC circuit's drop, or predicting server bottlenecks, dynamic systems run on strict mathematical rules. First-order differential equations provide the foundational logic required to decode those systems.